So today we will start to talk about layer 2 off-chain scalability. For my lecture, I'm trying to use all the illustrations to show you because it will be tough to dive into the source code to show you how it looks like. But end of the day, whatever I draw here is actually in the source code, right? If you don't want to listen to the illustration, you can read the source code. There's no difference. Again, right, just think back to the fundamental problems of the blockchain scalability. Just highlight again. So there's an assumption every node process all the transactions, store all the data, plus all the ordering of the transactions. That's a must for a layer 1. What if we push the transactions and the state to off-chain? You think back the sharding, right? The sharding is basically split the transactions into different shards so that we don't need to handle all the state together. But now the layer 2 is another idea, like push all the state and transaction to off-chain. And only broadcast the results on-chain to make sure whatever happening on layer 2, the state can be validated on layer 1. So that's the core idea for all the layer 2s. And when we talk about layer 1 sharding and scaling, we talk about scaling and also talk about blockchain interoperability. The other thing I didn't touch upon, because this is really what's happening now, is improve the client. The client, I mean, if you are running the EVMs, you have GETH, the gas. There are companies trying to improve the state and the transaction have a more compact encoding so that the client will be able to store more data in one block. So there's another optimization is still ongoing. I won't talk about that again, just because it's just too new. There's no standard yet. It's difficult to give you the lecture, which is the parallelization. And there are a lot of companies currently doing, they call it a parallel EVM. So the core piece of that is trying to process the transaction in multiple VM so that they're able to process the layer 1 faster. These two, if you really want to look at it, you can refer to RETH. Basically, they use Rust to rewrite the Go ETH. That's a client has been quite sufficient. They boost the performance twice compared to the GETH. That one is actually done by Paradigm. So that's the layer 1 scaling. I always use an illustration to explain what does layer 1 do. So layer 1 is like a supreme court. So everything, when they say yes, is yes. So when like the US Supreme Court sentence CZ to be in the jail for 4 months, that's a final deal, right? And also think about layer 1 as central bank, right? When the central bank tells you this is the balance of your account, that's a final signal, right? So that's what the layer 1 does. On the layer 2 scaling, on the other hand, we have, that's also what we're gonna talk about today, where there are two approaches. One is channel-based approach, the other one is a commit chain approach. So today we will focus a lot on the channel-based approach because that's the history, and also even though it's in the past, but a lot of use case and applications actually use the channel-based still nowadays. The reason being they are simple enough and fast enough. Other than the commit chain, it's very complicated. So think about layer 2 as the local court, right? So when they say you are sentenced, it doesn't mean you are final sentence. You have to make a record in the Supreme Court And even you as an individual, if you are in a local court, you are able to still sue back and ask the Supreme Court to verify or just sue back to your counterpart. And similarly, the layer 2, I always use the illustration, if you guys are from China, it's like a WeChat Pay and Alipay. They are not the central bank, but they make the transaction much faster and very efficient just because they are serving a lot of heavy loaded applications in the real world. But like WeChat Pay, the central bank or the government can always see you are illegal and I'll take back, right? So that's just an illustration purpose, how you can understand the relationship between layer 1 and layer 2. So why layer 2 is really exciting? Just because I'll talk about this one is because when we're doing a transaction on the off-chain, it's always set up and we are able to join the channel and then leave the channel. So that's basically the process of the layer 2s. Whatever happens in the middle, whether it's a channel-based or community chain-based, all these transactions happening only on layer 2. Only the final state come to the layer 1. That's why it's exciting, because imagine all my transaction initially supposed to happen in a central bank. Now I move to Alipay, WeChat Pay, or like in Singapore you have GrabPay, right? So all these are able to offload all the workload to the layer 2 and leave a much more non-congested pathway for the layer 1s, right? So that's why when we talk about scaling, this is really exciting scalability solutions. And again, it dramatically reduced the replicated computation due to we do it on off-chain. And basically, it will reduce the layer 1 latency and solve the issues of high gas for the layer 1s, as I initially talked about these issues on most of the layer 1s. And when we do that, we're still able to maintain the non-custodial security. You guys are clear of this concept, right? The non-custodial. So basically, the self-custodian, you own your assets, right? We're still able to do that with layer 2 solutions. And that means it's pretty safe and secure, and also the service, they intentionally make it live. If the state and all the transactions is not safe, we have a methodology there to guarantee safe. If the transaction involved, the parties involved in the transaction are not live, we will talk about this in this session, how the layer 2s are handling this kind of edge case. and also, right, so people talk about is all this state valid? So as I mentioned, it is. They are able to find a way to make sure all the state happening on layer 2 are valid are able to be validated on layer 1. And also there's a data availability when, for example, suddenly one of the parties in the layer 2 transaction gone like offline. How can you make sure the data is still available? Different layer 2 solutions have different solutions for that. We will also talk about that today. So these are a big chart of the promising layer 2 solutions right now, where we have a chain-based network and commit chain-based blockchains. So underneath here, so most of the channels here are for Bitcoin. We also talk about Bitcoin layer 2s. But most of the Bitcoin layer 2s initially for the payment to really accelerate the payment settlement, especially for the micro payment. So these are the few different type of payment channels we're going to talk about today. So there's Other development for now, which is more, they want to make BTC more generic. So actually from last year till now, there are about 200 plus BTC layer 2s live in the market. It's a mess. Some of the ideas are based on the bit VM to do scripting. Some of them using bring the idea from the Ethereum layer 1 and the layer 2s to BTC to make BTC layer 2 composable. There's no conclusion which way is better yet, because the way to tackle that issue is a little bit tricky right now. I don't think we can teach about that because, again, there's no standard. If you guys later on read about more BTC layer 2 we are not covered today, don't feel strange because it's happening now. And a lot of these companies raise a lot of money. It's happening now. But we won't talk about today here. And then we will actually go to the state channel, which is more for the Ethereum layer 2, the early version of Ethereum layer 2. We'll talk about in the details too with the illustration other than diving into the source code. So then if we have time, we will talk about the commit chain. One of the pioneers for commit chain is Plasma, where there's a one initiated by Vitalik, Ethereum Foundation called Minimum Variable Plasma, and there's another version declaring better than this version, which is Plasma Cash. So we will cover all this in this session. Hopefully we have enough time because we still have another guest who is Luis, a GP of 7X Ventures will come. Hopefully we can finish before he start his explanation of the company and the hiring plan. So the roll-up, I don't think we have time to cover today, but we will cover the roll-up, especially the optimistic roll-up and the ZK roll-up in the next session. I think it's a big enough topic to just talk about it in one big session. Yeah, so that's the plan. And we all start from the channel. I hope you follow with me. I hope you had enough, Dana have enough energy to follow with me because it's burning your brains today. Yeah, so as always, I want to go through the generic flow for the channel-based layer 2. Once you understand this generic channel workflow, you will understand most of the theories behind, so that just to help you understand this easier. So as always, there's a layer 1. On the layer 1, we multiple party or two party set up a channel. So that become the initiation of the channel. So when we doing the setup, the initial group is actually fixed. So for this kind of channel base, we won't be able to add other parties dynamically. It has to be fixed. And when we fix the initial group, we have to deposit initial balance. That's a must to have. As a matter of why, we will explain later. So then after that, all the transaction will bring into the channel. And all these transactions were happening among these few groups were happening in the off-chain, which is the channel. So all the parties will cooperatively agree and sign on the new state. So this has to be multiple party involved. If one party is offline, there's a way to dispute. We'll explain again in details on what will happen with that. So basically this procedure will happen continuously until we close the channel. So you may have a question here, right? What if, just now already mentioned, the one party or counterparty is misbehaving or not response at all, right? So we need to handle this edge case. So when this edge case happening, so there's a dispute period of time. Normally we fix the time too. Why? We will talk about why we have to fix the time later too. So then if such disputes happening, one party going offline, for example, the other party will trigger the dispute. So the online dispute is similarly to fault proof, but in another way, where the honest party, which, for example, for the offline case, the other party is still alive, will trigger this dispute, and that party can finalize the channel and close the channel. So as for how they close the channel, it will be based on the latest signed state or force the progression on chain with an unresponsive counterparty if that party going offline. So don't feel confused because I will have a specific example later to explain you again. But this again is a generic process when dispute happening, how the channel will handle the dispute. So just give you one example, it may not be specific. We'll have another specific example here, there later. But for example, if Alice now have evidence, for example, he knows the previous state, and telling the other party, Bob also has evidence. Who can win the evidence, right? So we take this condition as a standard example where only the fresher state and the other party who are able to command the authorized to execute the final state, otherwise can win the dispute. So there's always a party trying to dispute. The other party also may want to dispute if the other party also online. So whoever will win depend on who owns the latest state with the signature from both parties. I'll explain you in detail later. Don't worry about not understanding this part. Then after that we resolve the dispute. Then we close the channel, right? So one specific example I want to show you is the payment channel. As I mentioned previously, again, the Bitcoin Layer 2, majority of them are for payment, and majority of them are doing like a two-party or multiple-party channel. So the first one is called payment channel. So this payment channel is replace the state by the incentive. We call it a Spearman channel. So as for what is replaced by incentive, you will have more idea once we talk about that. So this Spearman channel is one way only. When the channel setup is assumed is only paying from A to B, always A to B, cannot be B to A. So that's how the initial Spearman channel was designed for. So then to improve this use case, there's another payment channel called duplex micro payment channel, DMC. So that actually resolved the issue of one direction, unidirection channel, payment channel. But in order to do that, they are not replacing the state by incentive, other they actually replace by the time lock. So I'll explain you in detail again later. So with that, right, we are able to do the bidirectional payment. And when we mention the time lock, it's actually the expiry time we always have to really set up the payment. So there's another type we also will talk about in detail. This is just an overview. It's called by replacement by revocation. So that's actually, I'm not sure whether you guys hear this or not, I think should be, is very typical and still, nowadays people are still using that. It's called Lightning Network. So this is replace state by revocation. So by doing this, by having this Lightning Network, we are able to do bidirectional, and also there's no expiry time. So why this is actually a kind of evolution, because the expiry time, what does the expiry time means? So when I set up channel, I have a dispute, and I assume there's only fixed amount of time these payments need to be settled. If more than this expiry time, the further payment won't be valid. So that's why with the Lightning Network, we resolve this issue, and there's no expiry time at all. And how they did it, we'll also explain later. They use hash time lock contract, which is HTLC, to connect the channels into a network. I'll explain in details too. So firstly, let's take a look into the first specific example of the channel called Spellman channel. So this is, again, it's only one directional payment. This assumption is like they are not able to handle bidirection. But let's look into the simple one first, right? So as we talk about the generic payment, the channel overflow, the first one, the workflow, the first one is always set up the channel. And when we set up the channel, if you still remember the generic flow, both Alice and Bob, actually in this case it's only Alice, because it's only Alice transfer the money to Bob. So that's why Alice needs to deposit enough Bitcoins into the network. And there are only two conditions for the Bitcoin can be redeemed by either Alice and Bob. So one is if a spend transaction is authorized by both Alice and Bob. For example, Alice transfer 0.1 BTC to Bob. If both parties sign this transaction, these two parties are able to redeem the BTCs. There's another condition where if the dispute time, which is T, timeout, Alice will be refunded. Whatever he transferred before, if Bob is offline, the assumption for the payment channel, the Spellman channel is, Spellman payment channel is the money will be refunded back to Alice. So give you again a specific illustration for these two conditions right here. So it's either the transaction can be deposited into Alice or Bob after the transaction, or if the T times out, the money will be refunded back to Alice. This is just an illustration for the left side of the ideas. And so once the channel is set up, the transactions will start where Alice will start to send BTCs to Bob. If it's difficult for you to understand why there's such kind of use case, you can think about a live streaming, right? So maybe Alice is watching Bob doing the live streaming, and so every other half an hour, Alice wants to pay something to Bob to incentivize Bob to keep doing the live streaming. So that's a use case. Actually, there are many more use cases for even just for one direction payment channel. And in this case, let's assume Alice sent 0.2 BTCs into Bob's wallet. And this UTXO will be like this, where by right, once Bob receives it, it will be 0.8 BTC on Alice's wallet and 0.2 BTCs on Bob's wallet. But for this direction, it's only Alice have the signature, not Bob yet. Bob's signature will happen later. So now let's assume Alice actually transfer another, Alice actually decided to cancel this transaction. In this case, Alice actually will decided to transfer another 0.1 BTCs into Bob, so that state become like this, right? It will continually evolving for all the payment until the last state, right? In this case, Alice already paid about 0.6 BTCs into Bob already, where Alice only left 0.4 BTCs, and Bob now has a 0.6. So let's assume this is the final state for all the payment from Alice, and they may plan to close the channel. Basically, live streaming is offline now. Bob is too tired, right? So how can we close the channel? So basically, Bob will sign the signature here, as you can see. So now we have the signature from both Alice and Bob now. Before that, Bob haven't signed because Bob don't feel like to stop the live streaming. He wants to continue, right? Now he stopped the channel, closed the channel by signing the signature into the transactions. And because we have the signature from both parties, when we push back the state to the layer 1, which is the BTC, the validator this is the final state, and I have this state have both signature from Alice and Bob. So they deem this as a valid transaction, final state from the channel. So as Bob, right, he definitely will have the incentive only close the channel by having the latest state, right? He doesn't want to sign here because he knows Alice will still pay that. So when he received the latest state and he wants to close the channel, he will start to close the channel. Another question here is like, can Alice broadcast a historical balance? For example, if Alice paid this, another 0.3 compare here, BTCs into Bob, but he agreed, he actually regret. So she decided to only broadcast this state to the layer 1. What will happen, right? And another question here is, because there's always edge case, right? The source code for the Spellman channel will handle all these edge case. So there's another edge case where Bob become not responsive during the channel operation, during the live streaming. So I'll walk you through what will happen if that case happening. So in general, we have a dispute period time of T for the two parties to dispute if those edge cases happening. And Alice will always get eventual refund if Bob is not responsive. Do you follow me? So for example, in the middle, we talk about Bob goes offline just now. If Bob goes offline, the channel, like Alice programming, will wait for a T time before Bob was able to respond. That response is actually a signature from Bob. If Alice cannot receive the signature from Bob, that means I assume Bob is offline. And because Bob is not responding in the program, the channel will be closed. And that's actually handled the edge case of Bob goes offline. Any question so far? Yeah, because the Spellman payment channel is only handling the continuous payment on one direction. It always increases. So the payment won't be decreased, right? There's no way for you to decrease unless you decide to close the channel. Yep. Yes. Yeah, something like that. So another good example other than live streaming or school fee is like a merchant and the vendor, right? So the merchant need to pay the vendors continuously. Or maybe some online game the player need to pay the gaming company continuously in order to play the game. So that's the context of this Spielman payment channel. Yeah. So with that, right, again, the issue is like it's only one direction, right? What if Bob want to pay back and need to pay back? So that's where the duplex macro payment channel is introduced. We always call it a DMC, where this payment channel we are able to do bi-direction payment. So the core idea is like other than only have one direction, we have two. Other than only have one channel, we have two channels now. One is to pay, the other one is to receive. And we won't go through the validation tree, but the idea is for the validation tree is I need to validate this. Both of the channels are valid, no matter it's in the final state of closing the channel or during the or starting of the channel. But basically the core idea of the validation tree is like replace the state, the initial state or final state or the intermediate state by time locks. I'll explain you what does time locks do here in the illustration later. And basically, from the high level perspective, the expired time means the time lock means there's an expired time for the newer payment to ensure the latest state will be redeemed first. You can read and pause here and read a little bit, but we will have again an example to show you. Yeah. So okay. So let's dive into a specific example how the DMC works. Again, as we always talk about, there's a setup channel. But differently to the Spielman channel, we have a time lock here, which is after 20 blocks. What does these after 20 blocks mean? It means if all the transaction goes well, we get a signature from both Alice and Bob. So the delta here just means a signature. So these two, the transaction will go to the script, the BTC script, right? And if after 20 blocks of the BTC blocks, there's no settlement for the channel, we will close the channel and refund the money back to Alice because the initial balance of Alice is 1 BTC. So then we have this time lock. Now you know what does the time lock mean here. It's just amount of time for the few blocks to be measured. So now let's assume Alice in this DMC channel, they pay 0.2 BTCs to Bob. So when this UTXO happens, we actually have we deduce the time lock by 1 because we assume the time lock for this channel is only after 20 blocks, right? So we deduce it for this because this one need to go to the next block, right? We deduce that amount of BTCs from Alice, and then these two gets this updated amount. But for this transaction, we only have signature from Alice. So basically, this transaction, again, will be encoded as a script on BTC. So next time Alice decided to transfer 0.5 BTCs to Bob, we will generate another state. For this state, it's 1 BTCs to 0.5 BTCs to Bob. That's where the output will look like. We assume these two happening in one block. That's where the expiry time is still after 19 block, just for illustration purpose. So again, it's in the script. So for this, right, it's still the same direction. And the reason we assume this still in one block is also because we deem this is one direction. We don't need to deduce it. But if we can also write an 18 block for another transaction, that's fine. But for the illustration purpose, we still assume it's in one block. We don't need to decrease it. But next state, when Bob transfer 0.1, basically pay back 0.1 BTCs to Alice, it will be in the next block for sure. So that's where for this UTXO, the output become like this, right? And because this is a direction from Bob back to Alice, this transaction's signature is from Bob. And if two parties decided to close this transaction or this channel, Alice can also sign the signature after receiving the UTXO from Bob. So with both parties sign the signature for this transaction, the channel now is closed. And so basically, the block will be updated to BTC here, and the validators will validate, oh, now I have the transaction, the final state for this payment channel, and this state of the payment channel has the signature from both parties, which is one of the conditions I can exit from the channel. Yeah, so again, right, so we decrease the time lock here, just because we want to ensure that there's a expiry time, less expiry time, and the latest state from the expiry time, which is the I plus 18, will be the ones we redeem and close the channel. Well, if there's another state updates from here, right? For example, Alice is not signing the transactions, then if Bob sends another transaction back to Alice, then the state will be updating to the next block. Yeah. Any question to this? So this is actually so-called the time lock, but replace the state by time lock to achieve the bidirectional payment. With this method, are you able to think about any way like people can dispute or abuse this payment channel? Actually, after so many years testing, this theory actually works if it's only for this kind of bidirectional channel, if you set an expiry time. If you don't set an expiry time, there's a black hole there. Yeah. So now I want to talk about the popular one, which is Lightning Network. The advantage for Lightning Network is this. With the implementation of the Lightning Network, we will talk about the details later. We are able to handle the finalizations instantaneously because we don't need to wait for the block information with the Lightning Network mechanism. And the transaction happening off-chain will be also have a lower cost if multiple parties is cooperative, and also the channel can keep open forever. Why? Because later on you will understand why we can do that. But again, right, with this Lightning Network, we don't have expiry time. It's more scalable because the on-chain updates were actually, you can handle thousands of transactions off-chain for one block time. Yeah, so basically that's an advantage, one of the advantages of a Lightning Network. And it's a little bit private because with the Lightning Network, we don't know the details of intermediate transactions until it's settled on the layer 1. But it's not that private compared to things like Zcash, because we know which party are involved, but we just don't know the details of the transactions happening in off-chain. And so mechanism the Lightning Network is using is not by time lock, not by the state, but other than it's by the revocation. And we will talk about what does the revocation mean later. But by doing that, right, we avoid the expiry time in a DMC, and we are able to also maintain two-direction payment channel with the Lightning Network. So that's actually a big step forward for the payment channel for BTC. And so the payment network is actually, we call it a conditional transfer. So where by doing the conditional transfer, they are able to achieve whatever the benefit we just mentioned. And the terminology for this conditional transfer is called hash time lock contract, HTLC mechanism to achieve that. We'll go through in detail now. So the call idea for the Lightning payment is for every state between Alice and Bob, definitely there's a deposit, initial deposit, it has to. And, but both parties or multiple parties sign a transaction only when the other party broadcast. And also when the channel closed or one of the transactions is broadcast, they are able to close the channel. So that's one of the big assumptions here. And also to authorize the payment, you need two steps here. The first step is both Alice and Bob authorize the new state. This is like I have the signature from both parties. And here comes the revocation, why we call it revocation. Both parties need to revoke the previous state. So remember the DMC, they don't handle the previous settlement, at all, because I have an expiry time to handle the edge case. But now, instead of having expiry time, by revoking the old state, I'm actually extending the expiry time, right? So that's why the Lightning Network is able to stay live forever, because we keep revoking the old state for both parties. And I'll give you an example. So let's assume there's a new state, which is 2. Now we have Alice paying Bob a certain amount of BTCs. We call this state as state 2B. And Alice signed this new state with her own signature. So once Bob received this state, he updated his own current state, which is his own wallet, right? And Bob updated the new state back to Alice, which means deduct amount of BTCs from Alice. And this new state will have a signature from Bob. And Alice will update her state to state 2A, right? Right now, we have two states, right? One is state 1A and state 2A for Alice. And Bob also have a two state, 1B and 2B. But now, we need to revoke the old state. So there's only one state being valid in this case, where we revoke the old state. So basically, Alice will tell Bob, I'm revoking this state of 1A. Please take note. And Bob doing the same thing. So again, each party have their own signature to revoke the state 1B. So then once Alice and Bob receive the revoke from both parties, the old state will be revoked. Have you follow me? I know it's a little bit tricky, all these examples. So all this state will continue because, again, this Lightning Network will be live forever. There will be multiple states in between, but every time there's a new state, all the old state will be revoked. So by doing that, again, right, we don't need an expiry time now. And so again, now if Alice wants to broadcast a revoked historical state. For example, she want to broadcast this to A, but the new state is not to A anymore. Bob can present the revocation evidence. For example, Alice want to revoke, telling everyone this is the state I'm having, the latest state. But now Bob can basically telling the layer 1 validators, I already received a signature from Alice where she tells me the state 1A is revoked already, and by right, she shouldn't declare and broadcast her own old state, right? So then Bob will win the dispute, right? So this is further to avoid any misbehavior for the Lightning Network. You guys follow me, right? Any questions so far? No? Okay, cool. Yeah, so underneath, right, I'll go through into more details on how all this mechanism works and give you specific examples. So let's assume like now Alice has 3 BTCs and Bob has 7 BTCs. They start to do transactions. And now let's assume Alice sent 1 BTCs to Bob. And this is a little bit tricky, follow with me. So there's 2 possible solutions for this transaction. The first transaction will be this 2 BTC will update the Alice wallet, become 2 BTC for Alice. And with this condition, Bob will have 8 BTCs. But there's another possible output for this condition where the 2 BTC will go to Bob. Why? If Bob is able to provide a secret where this secret, such that the secret hash equals to the digest H. If Bob is able to present this condition, it means Alice is doing something wrong or Alice is offline after a certain amount of time, which is T. So this case is really handling the edge case of Alice goes offline or Alice is doing a wrong dispute. So this condition can happen, right? Because it's UTSO, right? We lay out all the possible results for the transactions. So there's another potential output can happen where the 8 BTC will update to Bob's wallet first. If this case happening, the 2 BTC will update to A. If there's another possible condition will happen similarly to the first one, if Alice is able to provide the secret 2, where such that if the hash of secret 2 equals to digest 2. So if this become the situation, the 8 BTC from Bob will goes to A. So this again, right, is only this happening. The first one happening is only for B because the Bob will sign these transactions because the state will goes to Bob. Bob confirmed this transaction. The second situation is more like Alice want to dispute, where Alice will sign the transaction first. Do you understand this part? Okay. So now let's assume Bob sent 4 BTC back to Alice. And remember, we need to revoke the old state, which now we call it state S1. And Bob need to revoke it, the old state, which is S2. So again, so what does the revocation mean? It just means I'm revealing the pre-image of a hash digest, which is here, the hash digest. And this hash digest enables the counterpart to forfeit if the other party misbehave. So I just go through this example again, right? If, for example, Alice goes offline or declare the old state, she declares she still has 3 BTCs. So Bob now is able to doing the revocation for this revocation because Alice wants to declare she still have the old state, right? So she approved the hash digest of S1 state is the hash digest. So that's where I can prove the old state is now valid. And this is called revocation, revoke the old state. So in this case, do you think Bob can cheat by broadcasting the revoked state? Right. This is the state. This 7 BTC. Once he received the 8 BTCs, it will be 8 BTC. Do you think Bob can cheat by broadcasting the revoked state, which is the 8 BTC and 2 BTC for Alice? Which means Bob doesn't need to pay the 4 BTCs. Any idea? Do you think she can do that? He can do that? Yeah, the answer is no, because in order to have the final state, I need to have a signature from both parties, which in this case, if Bob wants to cheat, she doesn't have the signature from Alice. So only if Alice signs this state, we are able to close or settle the transaction. So, so basically this is an illustration. The new state is after Bob's transaction, Alice will have 6 BTC, Bob will have 4. The previous state is 2 to 8. And if Bob really wants to cheat, Alice will start to dispute, right? Because if Bob wants to declare this old state, and this old state, the old state only have signature from, which is here, because Bob wants to forfeit this state, right? So for this state, we only have signature from Bob, not from Alice yet. So that's why Alice can dispute, sorry, this old state is not valid because I haven't signed yet. And I only signed the latest state with my signature. So by doing this, right, Lightning Network are able to resolve the potential misbehavior from both parties or multiple parties. Hopefully, after all these examples, you understand all the different conditions and edge cases for Lightning Network. Yeah, if you have any question, feel free to ask. I know it's a little bit tricky. Yeah, so again, right, just to finish the dispute procedure, Alice will dispute with her signature on the latest state because she already received the signature from Bob, which let's assume is a new state. And Alice is able to win the dispute. So by having all these different edge case handling different potential dispute and multiple party signature handling the dispute, the Lightning Network are able to validate the state, right? Because you saw all the state has been updated from both multiple party signatures, and they are able to revoke the old state so that when they update the state, the final state, the finality, they can always make sure they have the latest state. And they do have an issue here because in this Lightning payment channel case, the data availability is guaranteed by multiple parties themselves on their own wallet. It's not by third party, right? If third party want to, if one party goes offline, the only case is just I can dispute. That's the only way. There's no other potential solution here to solve the issues. Like, what if the other party goes offline incidentally, right? So that's actually a big issue. Later on, we'll talk about how Ethereum layer to solve this issue. And so by having this Lightning Network, we are able to definitely handle all the transactions safely, as we illustrated just now. And there's no better way to make sure the liveness for multiple parties, and we can only force a response from other parties. If no response from other parties, we can only trigger a dispute with the latest state, right? So this is the issues or some of the advantage, if whatever you want to quote, for Lightning Network. Now I want to pause a little bit here, not for resting, but for you to think about these potential issues here. What if the malicious Bob refused to send the state 2A back to Alice? What do you think will happen? I already gone through multiple illustrations. I hope you have some idea in mind. If you can answer, it will be even better. What will happen? Anyone? You got an answer? No, you yourself? Yeah? No? Huh? Oh, really? Okay. Okay. Alice will what? Alice will send, you mean Alice will send the state? Yeah, go try. Yeah, actually, Alice won't send the revocation transaction over because by right, the next step should be revoking the old state, right? By right, based on the flow. But because Alice was not able to receive the updated state from 2A, the Alice also cannot continue to sign the further updates, right? Because she doesn't receive this state updated from Bob. So if, in this case, Bob wants to close the channel with the current state where Alice is not receiving the updated state 2A, Alice is fine because she had agreed to it. She had agreed with this, but she didn't really sign the Bob didn't really sign the signature of this, which means we can close the channel or continue the transaction with Alice's latest state, which is 1A, right? So if Bob tried to close the channel with state 1B, this here, Alice is also fine because she didn't really receive the state 2A. She can't update to 2A, right? And also, she didn't accept the 2A. I'll pause here for you just to go through this again, see whether this edge case is fine. Right? So Alice is actually fine, right? Even though Bob was not able to. I mean, maybe Bob purposely didn't send the updated state, but Alice is fine because the money is still on her wallet, right? Another potential issue, like what if Alice become the one malicious and she refused to revoke the state 1A? So basically here, right, she doesn't want to send. Basically it means she doesn't want to transfer the final updated state so that Alice will have less BTC and Bob will have more BTCs. Same thing, right? The Bob should not accept the state 2A because she doesn't receive the revocation of the state 1A. And he will also not, he only receive the revocation of the state 1A. Only after he received the 1A, he can continue. If not, these two will still keep the state with 1A and 1B, right? So in this case, no matter who is the malicious one, as long as both parties doesn't have a kind of handshake, they cannot continue the transaction. Even though they cannot continue the transaction, both parties are not really hurt, right? And I have another question here. Can we, do you think if we have multiple parties in this case, now we call it Alice, Bob, Charlie, and David. Do you think we can set a routing payment through the existing payment channel without creating a new channel on-chain? What I mean here is like do you think we can provide a hop, like here to here, here to here, to here to here, so that we don't need to set a direct payment channel between Alice and David? Why we talk about this, because if every time we create a new channel for a new two parties, it's expensive because every time we need to set up a channel. And for the Lightning Network, if every time there's a new party joins in, we set a new channel, it will be like millions or billions of channels existing. That will be crazy, right? And do you guys know an answer? Like, do you think we can do that, a hop? So actually, with the previous mechanism, we can't. That's where Lightning Network introduced a transfer called conditional transfer. And what does the conditional transfer mean so here we take Davi, for example, where Davi has used a random number. He used a random number to hash it and generate a hash value or digest here. And this digest will send back to Alice. And Alice, right now, with the conditional transfer, she won't send one coin or BTC, whatever you want to call, directly back to David. Instead, she sent a conditional transfer. That's where we got this name called conditional transfer. So what does this mean? So if Bob can reveal the pre-image, which is the digest here, before the time t, this is just a time we set up in the program, then Alice can get the coin. So that's the condition. Only if Alice receives this pre-image of the hash, David will be able to receive the coin. If David doesn't reveal the hash, Alice will still hold the assets. So that's conditional transfer. So once Alice reveals that, the one Bitcoin will be transferred to David. So later on, I will have a multiple party conditional transfer to explain you in more details. But for this conditional transfer, from Alice to David. What if Alice refused to send the coin? If David already revealed the image, the pre-image, based on this conditional transfer, Alice should send the coin, right? But what if she decided not sending this coin? Actually, if that's the case, the Alice conditional transfer statement, which is this one, will be broadcasted to the network on layer 1. And this condition will be forced to execute, so no matter what. So by doing that, right, we make sure once the condition is fulfilled, Alice has to send the money to David. The reason we have this conditional transfer is for the purpose of multiple hop, where we're going to discuss now. So after this, we'll have a rest. So Alice now, let's assume, want to send to David 1 BTC. And we need to set up the receiver being Dave, and the sender is Alice. So each hop, like Bob and Charlie is the hop, they commit to the conditional transfer, which means only when Charlie received the pre-image from David, Charlie will send 1 BTC to David. So they commit to this conditional transfer. Everyone commit. And so this is the things they are committing, right? So basically, all the conditions need to be committed for this multiple party hop transfer. And the BTC were founded by Charlie in this case, right? Because the reason Charlie can commit to this condition is Charlie himself has enough BTCs for the commitment, right? And this is between these two parties. So in order to get the money from Alice, so now Charlie need to set another condition transfer with Bob, right? Similarly, only when Charlie received the hash image, the pre-image of the hash number, Bob will transfer the BTCs to Charlie. That's another condition Bob is committing. And similarly, Bob is asking Alice to commit on this condition transfer, right? But remember, in order for this, still remember the the purpose of this multiple condition transfer, right? The final result we want to achieve is Alice is now able to send Dave 1 BTC. If we don't have this hop, because Alice doesn't have a direct channel with David, she cannot send this transaction directly to David. But notice the T1 here, and T2 here, and T3 here. So I just want to highlight what does this mean. So the T1 means after period of time T, if David cannot receive the money 1 BTC from Charlie, David or whatever will receive the 1 BTC. So that's the expiry time, right? So there's an expiry time here for this multiple hop, for the condition transfer. But this expiry time is purely for the multiple hop conditional transfer. So in order for this hop to work, T1 should be longer, T1 should be shorter than T2 and shorter than T3. Why? Because if, for example, T1 is longer and T2 is shorter, Charlie already received the money from the 1 BTC from Bob. They closed this transaction. But because this T2 is shorter, and Bob actually Charlie doesn't need to send the transaction to David, and Charlie become the one's own 1 BTC here. So there's a potential condition happening like this, but doesn't mean it will happen, right? There's other mechanism to guarantee, but in general, we set expiring time based on this condition. Yeah, so let's see, right? If the hash time log contract transfer happen hop by hop, and continuously each party reveal the pre-image from reversely, from David to Charlie to Bob to Alice, so that they can receive the 1 BTCs from the previous hop. And this becomes the procedure to receive the BTC. And by recursively doing this, the multiple hop, or David, end of the day, will be able to receive the BTCs from Alice. So edge case happening now. What if Bob refused to pay Charlie? Right? Just now we already mentioned a case. If Bob doesn't want to pay Charlie 1 BTC after Charlie revealed the pre-image to Bob, what will happen? Any idea? Still think back to the old workflow for the channel workflow. So actually what happens is, there's not a case. What if Bob refused to pay Charlie when Charlie revealed the pre-image to Bob? The same thing. Actually, the dispute will happen because Charlie is supposed to receive the 1 Bitcoin, right? But now Charlie didn't receive it. He will release a dispute to the layer 1 validators, and telling the validators, I already had Bob with me, Charlie already have a conditional transfer, but now Bob doesn't want to send me the 1 Bitcoin. So during this dispute time, now Bob is forced, because the validator already received the commitment, which is the signature from Bob on this condition, but Bob doesn't agree to pay 1 BTC to Charlie. So now Bob is forced to execute because he already commit to the layer 1 validators, right? And everyone know, because it's already broadcasted to the network on this logic, right? So during Charlie's dispute, so everyone knows this condition already, because everyone knows the condition is already committed and signed a signature by Bob. And Bob has to now claim the Bitcoin to Alice. And then Bob will send the BTCs to Charlie. So to give you further idea on why this T1 need to be longer than T2, basically if David could cause Charlie to lose money if T1 is longer than T2, right? Because if T2 is longer, think about this, right? If T2 is longer than T1, and Charlie was not able to receive the pre-image from David, and because of that, Charlie also doesn't have the pre-image from, Charlie can also not send the pre-image to Bob. And this T2 already expired. So when the T2 expire, what Bob has to do is transfer one BTC to Charlie, right? So just to avoid this happening, because this is a multiple hop, so the condition has to fulfill from one by one. It cannot be in advance transfer the one BTCs. T2 has to be shorter than T1. Yeah, just now the students was asking why there's a DMC. The DMC is really a solution in the middle. Before Lightning Network become mature, the blockchain is always like that. Just always iterate, and the solution won't be the final solution at all. Even there are companies trying to improve the Lightning Network because it can only do payment, right? There are still scripts. You can do a little bit more than that. So that's why even Lightning Network may not be the final solution. But the good thing is like it's evolving. And for the Lightning Network itself, the good piece of that is you solve the issues of the DMC, right? And you don't need to set up channel for each pair-wise transfer. It will be there forever. You don't need to set up the channel for these two parties only. And also, because the hop mechanism, now we have a routing marketplace, right? When you want to send another party without direct channel, you can using the routing marketplace to route the payment to the final destination. And everyone can provide collateral, which is the deposit of the BTCs, to be part of the routing marketplace. And I know there's companies doing that. Some of the privacy-based social medias, forgot the name suddenly, but by doing that, we are able to earn quite an amount of income. And so it optimistically fast if there's no dispute. If there's a dispute, yes, there's a delay, but in general, it's pretty fast. That's why they call it Lightning Network. Again, right, there are still issues for Lightning Network. That's where a lot of research are ongoing to improve this. But today we don't have time to talk about those. But the issues for the Lightning Network is like there's a free option to create and hold on to conditional transfer and waste liquidity, right? Imagine all these conditional transfer, you have to have the hops in the middle to hold the collaterals in order to become the hop. That's a very expensive way to do that. You can't imagine if nowadays I want to transfer money, cash, or fiat from one party to another party because I don't have a direct bank. I have to ask like someone in the middle to hold the assets. Well, actually, some banks are doing that like that, but for a day-to-day transaction, it's not like that, right? And also the other issues like heavy collaterals, right? A lot of BTCs need to be deposited for the multiple hop. And if it's four hops, that means 4 times of the collaterals needed for the transfer. And if the worst case happening, the waiting time for the final settlement is T1 plus T2 plus T3, if you still remember that hop chart. So that's for BTC. Now we will talk about the state channel for Ethereum. That's first layer 2 solutions category for the Ethereum layer 2, where other than like all the Lightning Network, we need to set up the channels. They utilize the smart contract, right? Because with smart contract, definitely not like the script in the BTC, we can do many more. So by doing that, we are able to use the arbitrary state in a channel, including a balance in a payment channel, and also including, later on we will talk about, it's called replace by the state by version. So what does the version mean? It means it's not the payment state anymore. It's, for example, later on we will have an example for chess, the chess game. So now we can we also can do the chess play, bring up the chess play game onto the layer 2, other than just payment, right? So later on we will have an example to show you what does that mean, like replace the state by version. And also by having the state channel, and also by doing the replacement, the state by the version, now we don't need to do bookkeeping to keep all the old state and revoke all the old state. The storage is much less. So, I'll show you a specific example on how, again, workflow works for application-specific state channel. So later I'll also show you a generic state channel, other than just only for one application. But in this example, we will talk about one application state channel. So again, the same procedure, if you still remember the channel workflow, these two parties in this example need to set up the channel. And other than the payment, now we use a chess game as an example. The rules for this chess game is winner will take 10 Ether. Now, because it's on Ethereum, we talk about ETH other than BTC, right? And both parties, when we set up the channel, Alice need to deposit 5 Ether and ETH, and Bob need to deposit the similar amount. So when the setup happening is not to write into the script now, it's actually write into a smart contract on Ethereum. Right, so that's where we show you the smart contract kind of thing there. And so again, the application-specific state channel, we, other than record all the payment state, we record the logic state. What does that mean? The logic state is like, for example, the chess, we move from E4 to E5. That's a state for the whole chess game transaction. And let's record this state become SI I. So on the I's transaction, the state for this transaction is SI. And Alice again signed this signature telling Bob, I agree, I already placed the chess on this position, right? And similarly, Bob has acknowledgement back to Alice, and I agree the state is updated. And to do the next step, I have a new state for the chess game, the chess, right? So now the new state is the Bob will move from B1 to H7 for the chess. So that becomes the new state, which is only signed by Bob for now. So each new state is only, is actually unanimously, which is two-directional, agreed. It's only one directional agreed by either Alice and Bob for the current state, right? And for now, we increase the counter. So think about this is the version, right? So this version, it's only moving this chess, and the new version move the new chess, right? So we increase the counter to increase the version. And this is, again, to prevent a playback attack. So do you guys know the playback attack? Basically, I want The playback attack is like I don't agree this new state and just agree this old state, right? So what if Alice in this condition regret? She find out, oh, I don't want to move ahead for the status I, and Alice want to close the game with the old state, for example, state I minus 5. So she just want to use the old places of the chess to be the ones to declare that's the latest state to the network. So again, right, I want to just to highlight again, right, all this block here is on the layer 1 validators, and the state channel were happening in the scripts. Similarly to Ethereum, all the transactions were happening in the off-chain on a second layer, and but the block for Ethereum will continue, right? Yeah, so by then Alice will declare the old state, right? And because Alice is going to trigger this state, and the dispute is actually triggered. And again, there's a dispute period time, like whatever the other state channel or channel has been doing. During this period of time, that's a counterparty, which is Bob, his time to dispute, where he dispute, I already have the signature for SI and I, where I got signature from Alice, and Bob also signed the signature. So by right, this should be the new state for the chess game. And because of Bob's evidence of this, Bob is able to win the dispute, right? So that's basically, this is the methodology on how this specific state channel has been using to avoid Alice cheating. And then the dispute is resolved, right? So another is like Alice saw Bob has checkmated, right? So basically, after this step, Alice or Bob will win in the SI plus 1 state. So Alice, because she saw that she is not responding on this case, so what will happen? So if Alice is not responding after the dispute time, after the certain period of time, Bob is able to telling the layer 1 on the smart contract on the layer 1 where this state has been signed, and now I have a new state, like I just moved the chess. And because there's no response from Alice, by the logic of state channel, that's a time for dispute. And because Bob already showed this as the current state of the chess game, Bob is able to win the dispute because Alice is not responding, even though potentially Alice is able to win, but because Alice is not responding, we actually, the state channel basically will take the 5 ether from Alice to Bob, then Bob is the winner. So Bob basically forced the game to continue on-chain by broadcasting the latest state, which is already signed by Alice. Yeah, so that's the application state specific state channel I want to highlight. So there's also some other versions of state channel. I won't talk too much due to the time constraint, but you can read more about like what is a virtual channel. So the virtual channel in the layman term is it trying to improve the HT hash time lock contract for that channel by set up a virtual channel directly, and so it only involve the intermediary hops during the opening and closing of the virtual channel. When the real transaction happening, the intermediate channel won't be involved. So that they don't need to cooperate in the middle to have the so-called conditional transfer. So this is a way of improving that payment channel on Ethereum. So you can read more about how they achieve it in this paper here listed, if you are interested. So I won't go into the detail. So the other one is a sprite channel. So this one, the core idea is to use smart contract to reduce the worst case collateral lockup time. So this again is another way to improve the HTLC payment channel, multiple hop conditional transfer. Because the worst case, if you still remember the hop, multiple hop from A, B, C, D, right? The worst case time is T1 plus T2 plus T3, which is like a delta times the length. Delta is the roughly the time frame between A and B, B and C and D. So by having the sprite channel, they are able to reduce this worst case scenario, and they also allow not fully deposit of the collateral, only partial deposit to the collateral, so that they reduce the time for the worst case to be only T plus L plus delta. Again, I won't go into detail, just considering the time. You can read more about this paper here. I won't say this is not a mainstream. I would say different solutions is for different use case. Even when you're doing your final projects, or when you are in a company doing your own projects for the company, I think you should choose the best solution based on the specific use case, other than use a generic solution for anything. Just because different resolution have different advantages and disadvantages. So last but not least, I want to talk about generalized state channel, because just now we talk about application-specific state channel, which is the chess game. What if in the state channel, it's not only one game, it's multiple games or multiple apps in the channel? So how can we do that? That's actually the core issue the generalized state channel is trying to resolve. And the idea behind is to initiate the new smart contract off-chain, right? Remember the application-specific channel, we actually set up the smart contract recording the final state on layer 1. But the generalized state channel, the idea is initiate a new contract every time it's a new application off-chain. So how can you map that function of the off-chain smart contract, because it can be anywhere, right? So in the Ethereum, there's an opcode called create2. There's a one way to doing the mapping of the function of the smart contract at off-chain. So there's another way, which is it's called contract registry mechanism, such that the contract can be deterministically addressed and referred to. So basically, you can just call that function from the main blockchain. And the other idea is just to commit to the contract code. And when you call this contract function, it will start to execute that contract off-chain. And that's the core idea. So if there's a dispute or misbehavior happening for this kind of off-chain logic, so we will force the off-chain smart contract deployed to the on-chain, to the main Ethereum. and with the latest signed state from both parties or multiple parties if multiple parties involved. That's one resolution, because end of the day, the main issue for the application-specific state channel, if you still remember, is the dispute, right? I need to get the latest state from the off-chain transactions. If the state is fine, right? Because for the application-specific state channel, I know who are the one holding the latest state. But if it's an off-chain smart contract, the logic can be anything, can be multiple games. How can you know, even you have the latest state, how do you know which party have that state, right? So the first method for this dispute is to just deploy the smart contract to the main contract so that I can trace back. So another way is to collapse from the virtual channel. So then play out a channel here. So just for example, right, if the logic happening off-chain, in an off-chain smart contract, I don't know what's happening. And one method to do that, if there's a dispute, is I actually know where the dispute happening, and I use the intermediary to replay the transactions if I know the state from the off-chain state. Any question? So again, I won't go into the details. If you want to know more about this generalized state channel, you can go through Perot network. This is a popular generalized state channel for this resolution. And you can also go through some of the presentations from Christina on YouTube. It explains you more detail on what does those means. So considering the time, I won't go through that too. Then for the channel-based network, in summary, the goal part is like we can have instant finality, right? So all the states are instantaneously settled. And in most cases, the cost is pretty low. And also is somewhat private because the intermediate transaction is not updated to the main blockchain until the final state. And it's suited for a fixed group of people, parties. If you want to have a multiple party, again, this is not a good solution for that. So the disadvantage for the channel-based network is like, again, you need to have a high collateral lockup. Remember, both Alice and Bob need to deposit 5 Ether individually. It's not efficient on the capital efficient wise. And so also there's assumption like both parties need to be online. If either one party goes offline, we goes into the dispute procedure. And again, it's user's responsibility to hold the data available other than third parties. And so similarly to the HubSpot architecture, the multiple hub and virtual channel is a little bit complex during the dispute resolution, right? So after, I think I'm going too slow. So after all that, right, we already finished the channel-based network. We still have another small piece here to cover. Hopefully we have enough time before Luis comes. So next we'll talk about commit chain. And underneath the first one category of that is plasma. Let me double check. Okay. Yeah. So on a side note, the routing of the complexity is driving the channel network into a HubSpot topology, because if there are too many hops in the middle, the network will become too complicated. That's where the majority of the channel-based network are just the HubSpot network topology to make the transaction easier and faster. And the instant finality is good, but the high collateral lockup is really a bad thing, because when you have that requirement, that means it will be less decentralized. So for the term, it's called permissionless. It won't be that permissionless due to these requirements. And so do you think with that, right, can we relax the finality into the eventual finality to make layer 2 more permissionless? So what does that mean? Do we have a method to reduce the high collateral deposit to make the layer 2 more decentralized? So there's other tribe before the plasma, which is a sidechain. We won't talk too much about this. It's easier to understand. Just briefly talk about that. So basically, there are two blockchain in parallel, for example, BTC or BTH, right? So these two can actually, using the two-way peg to transfer the assets or BTCs in between. What does that mean? It means if I want to transfer one BTC from BTC to BTH, I can lock my assets in this wallet set up by BTH, and I generate a new BTC, let's call it SBTC, mint a new BTC on another parallel BTH. So that's where we are able to peg back if we want to generate new assets from the another parallel blockchain. But before we mint this, right, for the sidechain, we need to burn the old assets from the old blockchain. So that's the how sidechain in brief has been doing. But there's an issue for that, which is in order to doing the lock of the assets and the burning of the assets, the key actually belong to this party who own this blockchain or operating this blockchain or from the operators. So this become non-custodial. This become custodian, which means the assets is controlled by the other party, not by the customer itself, right? So basically, the case for this is more like those companies doing the cross-chain. They are the ones holding the assets. They decide whether I want to burn the assets or not, right? So do you think, is there any way for us to have a non-custodian sidechain? So that's where the commit chain was born. And to run you the generic commit chain workflow as what we always do. So the commit chain, there's always a manager contract, smart contract, or you can also call it the East Bridge contract on layer 1, which is Ethereum. And different to, if you still remember the shard chain, there's a validators randomly allocated to the multiple shard. The commit chain in general, the validator are not randomly picked. They are actually fixed. And whenever there's new state happening on layer 2, all the transaction state is actually become part of the Merkle tree for layer 2. So then, other than doing the dispute or generating the block on the layer 1. Now with commit chain, we actually padding all the block on layer 2 directly. So that become another blockchain on top of layer 1. That's why we call it layer 2. So imagine all this state. I'm not disputing with the layer 1 anymore. I'm maybe dispute on the layer 2 because I have the validator in place to do the dispute. So by doing this, right, I offloading not only the transaction but also the dispute process to layer 2. But in order to maintain or derive the security from layer 1, we periodically update the whole Merkle tree or part of the Merkle tree, which in general we only commit the state root of the Merkle tree from the layer 2 back to layer 1. And so we are continually doing that until a withdrawal happening. So when withdrawal happening, so that become the for that transaction we may end that transaction procedure, but doesn't mean the layer 2 is closed. The layer 2 will be always there. So as I mentioned just now, this commit, right, it can be state root only, or can have all the transaction included to commit. So basically that different kind of commit back to layer 1 differentiate the plasma and the rollup. The plasma actually only have the state root commit. And yeah, Luis is here, right? Okay. Yeah, so then for the rollup, we will have all the state root and all the transactions data on chain. So if you saw some places talking about this, where do I store the data, the core data for layer 2? In general, the rollups, they send all these transactions back to layer 1 still. But this may not be the case anymore for some of the rollups. So I don't think we have time in this lecture to talk about that, just too new. But there are, right now, definitely there is companies trying to even make the transaction off-chain. So another question is like, who can be a validator in the commit chain, right? So again, here we call it layer 2. We can also call it commit chain. And who will be the validator here? If it's not the validators on layer 1, right? And how many of them is required in order for the commit to be fair enough, for the dispute to be fair enough? So in general, mostly anyone can put up enough security deposit to be in the East bridge contract to be the validator. And in general, the requirements for the deposit from 1 Ether to 100 Ether plus. So if there's a dispute happening, again, this is a generic workflow. It's not a specific protocol. If there's a fraud happening on some of the states on the layer 2, there's a dispute. And the dispute actually the fraud proof will be studied. And these fraud proof will different rollup, different plasma will have a different mechanism we'll talk about later. But this is a little bit different to the sharding dispute. If you still remember, the shard dispute need to go back to the beacon chain to dispute. But this dispute actually was doing it on the layer 1 too. Similarly, you can think about the layer 1 as the beacon chain in this case. But there are actually some difference. So what's the difference? So this is the comparison from Vitalik You can read in details on the Vitalik's blog here. But in general, the difference for these two, commit chain and the sharding, because it seems quite similar on the architecture perspective, but it's actually different in the way like the sharding requires tight coupling, right? You still remember the shard, how I generate a shard, how I randomly pick the validators. That logic itself is already different to the commit chain. And also the commit chain is decoupled from the validation of the layer 1 chain, right? Because the validator are not from the Ether, the Ethereum validator. It's randomly drawn from third parties, right? So that's some of the key difference between the commit chain and the sharding if you want to know more about that. And in general, the sharding is trying very hard to ensure the total validity, availability of every part of the system, but the plasma, in this case, rollup is a different story, right? The plasma, in this case, they accept the local faults, but try to limit their consequences within plasma. So finally, I think I saw Luis is already here. Hi, Luis. And I will try to spend the last 10 minutes to talk about partially about the plasma. I don't think I can finish it. We will piece plasma, the rest of the plasma together with rollup later. So for plasma, right, the potential issues, the things the plasma was trying to do was really scale Ethereum in a better way of state channel, where we are able to deploy a smart contract on layer 2 and make sure whatever happening on the plasma chain is able to have the logic off-chain on the layer 2. But there are many discussions and a lot of disagreement on how plasma was initially shown up. And initially when the blog came out from Vitalik, everyone was excited. But after so many trials, so many versions of the plasmas, we figured out seems it's not possible to deploy a smart contract on plasma. At the same time, we are able to make sure the computation integrity is there. Why? Because for plasma, it's difficult to guarantee the data availability. And later on, we'll show you a little bit details why that's the case. And the other issue is like if multiple parties trying to withdraw Ether from plasma, it will be quite challenging. You can read more about the discussion in the link. But in general, there's two plasma we'll talk about, right? One is the minimum variable plasma proposed by Vitalik. There's a plasma cache proposed by Andrew Miller, I think. So for plasma, minimum variable plasma, there's a plasma contract set up on Ethereum as a bridge, if you still remember the general workflow for the commit chain. And the plasma chain, which is now from the commit chain become plasma chain, is maintained by the operators of the plasma. You can also call it the validators. And the minimal variable plasma, they use UTXO model for simplicity. They are not using the generic smart contract and the ways Ether has been doing. So the UTXO, in general, the workflow is you deposit in the smart contract on Ethereum and add balance again back to the plasma chain. And multiple transactions will happening, it will be processed and include in the plasma block by plasma validator. So the plasma validator will validate before or even after the transaction happening. And the plasma block headers will get a commit on the plasma smart contract. And the transaction inside the block considered to be confirmed on the plasma chain. So the exit and withdraw by will happening only if there's a proof for the UTXO to the plasma contract after the certain period of challenging time. If there's no dispute happening or no successful dispute happening, basically you are able to prove the transaction. UTXO is able to be claimed. You can withdraw the money from the plasma chain. Then the plasma chain and the smart contract will release the fund back to the user who are exiting from the plasma chain. So by doing that, where the user has to frequently check the plasma chain, and if there's an invalid block happening on the plasma chain, the user is not able to exit. But if there's no invalid block, the users are able to exit. So I have a few questions here. I will just show you the answers considering the time. So what are those has been installed in the plasma contract? So those actually are the identities and securities deposited into the plasma operators, basically the ETH. And all the plasma block headers will be also in the plasma contract. Remember, the plasma chain is only have the block headers, the Merkle tree block headers and root in the smart contract. It's not all the transactions, right? And also, it will store the logic for handling user deposit and the withdraw and dispute. So that's basically what the smart contract of Plasma has been doing. That's all it does. It basically, considering all the edge case, if you are doing all the dispute, doing all the deposit and withdrawal of the assets. And another question here, like how could user enforce a timely balance top-up in Plasma chain when he deposit? So the answer is when user deposit to the Plasma contract, the contract will immediately add one block into the block headers into the smart contract. And because the smart contract is representing the canonical history, because it's a linear confirmation for the block, the Plasma operator must include the single transactions into the block so that the balance will be able to update it immediately. So that's basically how the Plasma initially is designed. So in terms of the life cycle for the payment in the Plasma, again, so I didn't give you the illustration for Plasma just because the chart is really difficult to draw. If you saw all the channel chart is difficult to draw. Another reason is like the Plasma is not popular anymore. It's kind of dead. So just you just know some of the information on what does Plasma do. So the life cycle of the payment in Plasma chain is basically Alice create a transaction and sign it. Then it's sent over to the operator of the Plasma. So the operator will verify this transaction and put the transaction into the next block together with other transactions if all the other transactions happening in parallel, right? And the operator will commit the new block headers to the Plasma contract on Ethereum. And now the Alice transaction can be considered as confirmed. Only by then, this transaction is valid, right? Just think about it. I didn't draw it, just considering the complexity of drawing that. But Alice still needs to send a confirm message, which testify her confirmation of the transaction to another party, which is Bob in this case. and Bob now safely accept the payment and continue, and then he can send the transfer to other parties. So there's a confirm message. I little briefly tell you why there's a confirm message needed for Alice. So by doing all this logic, why Plasma is secure? Do you think the operators can steal the money? So if actually the Plasma operators commit an invalid block, because they can do that, right, as an operator. So if he mint or generate a new token on the Plasma chain himself, and he want to withdraw the money from the Plasma chain, then the user actually can notice this behavior. Why? Because the Plasma contract itself has a dispute mechanism there, where the users can dispute the mechanism if the operator is trying to do badly. And the Plasma contract also handle the withdrawal in the timely order for the UTXO. Remember, the block will be just adding subsequentially based on the time. And if the block comes to the operator's withdrawal claim, the contract is already drained with no balance because it's UTXO, which means for the UTXO, the one receiving the money has to have a transfer in, right? Because it's UTXO. If you generate a new assets from nowhere, the contract will notice there's no input from the UTXO. So that's definitely an invalid withdrawal. So that's where the operators is not able to do that. And last but not least, do you think the user, for example, Bob, can withdraw more than what he ever owns on Plasma chain? But when Bob attempts to withdraw the money, he submits a UTXO, which is more than what he initially owned. But there's no one actually transferred to his wallet. The exit transaction will automatically start a challenge period of 1 week. So this 1 week challenge period time is initially from Plasma chain. Later on, when we talk about optimistic rollup, I will have a better chart to show that. There's a challenge period similarly to Plasma chain. So during this 1 week, so anyone can submit a fraud proof to basically check all the UTXOs. So anyone interacting with Bob before, the third party can utilize this 1 week dispute time, which is very long, to dispute this transaction is invalid. So by doing that, Plasma chain is able to, in a way, to solve the issue of invalid withdrawal from the blockchain. So last but not least, before I hand over to Luis prepare, why there's a final confirm message from the Plasma chain is because all the tokens in Plasma MVP, minimum variable Plasma, is fungible. There's no non-fungible assets on layer 2 on Plasma chain. And all the exits are based on the time order. So the order for all these assets, among all these orders, when the assets, they are processed based on the time. It's one block by one block. And the block will be held by the operators. Think about this. So basically, the operators is able to withhold the block. So when the block withholding occurs, the operators will intentionally they will not publish a block or even delete the publication. He can do that. That's basically what it means for block withholding. And when the block holding happening, the user trying to exit based on incomplete and incorrect information of their transactions, the users won't be able to exit. So when the user can exit, only when the user receive a confirmed message from the operators. And because of these complicated procedures, and because of these, like whoever as a validator can hold the block, that can make the data unavailable, right? That's the most challenging issue for Plasma MVP, and that's why the Plasma as MVP was a fail to try. And even till now, there's no running network for Plasma MVP. But that was a good initiative that paved a good way for rollup. We're going to talk about in the next lecture. So if you want to know more about the MVP issues, you can go through this link. And I don't have time to go through the Plasma cache. We'll talk about in the next session.